Picture the last moment of daylight. The sun has just dropped below the horizon, and in that bruised purple sky you see it. A single star, the first one bold enough to show itself, burning steady while the rest of the world still glows orange. You are looking at a sun, another sun, a nuclear furnace containing roughly 370,000 times the mass of our entire planet, radiating heat and light and X-rays into the void between worlds. It is the closest star to Earth that is not our own, and it is so far away that the light you are receiving right now, the photons landing softly on your retinas in this quiet evening moment, left that star 4 years and 3 months ago. You are not seeing the present. You are seeing deep history. The star you are watching may have changed, may have flared, may have done something extraordinary, and you will not know for 4 more years. How far is that? How far, really? And here is the question that nobody tells you to ask. Once you understand the distance precisely, once you work through the actual numbers, the physics, the engineering, the biology, the mathematics of what crossing that gap would demand, does the distance become more manageable, or does it become something far worse? There is a particular trick that language plays on us when we talk about the cosmos, and it operates most powerfully when we are discussing something that sounds almost reachable. The nearest star. The phrase implies closeness. It implies a relationship between two things that are not impossibly separated. It implies, at some deep irrational, pre-rational level of the human brain, the part that evolved on the African savanna, calibrating distances in meters and kilometers, that the nearest star is something like the nearest town, the nearest mountain range, the nearest ocean. It is not. But before we can understand how wrong that intuition is, we need to establish the ground truth of what we are actually talking about. We need to name the thing, measure it, and set it properly against everything else we know about scale and distance and the human project of exploration. Because only once we have done that, only once we have grounded ourselves in the real, measured, verifiable numbers, can the true scale of the problem begin to crystallize. The nearest star to Earth, excluding our Sun, is called Proxima Centauri. It sits in the southern constellation of Centaurus, and it has been known as the closest stellar neighbour since the early 20th century, when Robert Innes, a Scottish astronomer working at the Union Observatory in Johannesburg, identified it in 1915 by comparing photographic plates and noticing a star with an unusually large proper motion, meaning it appeared to shift position relative to background stars more than almost anything else in the sky. Large proper motion in stellar astronomy is a reliable indicator of proximity. Things that are closer to you appear to move more, a principle as ancient as watching trees blur past a car window while distant mountains barely shift. Innes named the star Proxima Centauri, from the Latin for nearest, and within a few years of subsequent measurement, its distance had been confirmed to be the smallest of any star outside our solar system. That distance is 4.2465 light-years, or if you prefer a number with more weight to it, 40,208,000,000,000 kilometers, 40,208,000,000,000 kilometers. Written longhand, that is a number so large that the human brain simply cannot process it as a meaningful quantity. It is a number you can read and speak aloud and immediately forget, the way you might read a city's budget figures. The digits enter, they register briefly as symbols, and they evaporate without leaving any real impression of scale. So let us try a different approach, because understanding scale is not a trivial academic exercise, it is the entire foundation of what follows. A light year is the distance that light travels in 1 year, moving at 299,792 kilometers per second. This is, by any measure, a staggering velocity. Light crosses the distance from Earth to the Moon, 384,400 kilometers, in approximately 1.3 seconds. It travels from Earth to the Sun, 149,597, 870 kilometers, in about 8 minutes and 20 seconds. So when we say that Proxima Centauri is 4.2465 light-years away, we are saying that even light, the fastest thing in the universe, travelling at a speed that makes bullets look stationary, requires 4 years, 2 months, and roughly 17 days to cover the gap. And light cannot stop. It cannot decelerate, send back a signal, or perform a survey. It simply passes through. The journey takes 4+ years at the maximum speed permitted by the laws of physics, and there is nothing we know of in the universe that can do better. Now let us come at this from the opposite direction, from our own speed rather than light's. As of the current day in 2026, humanity has exactly 2 objects that have left the solar system by the standard definition, meaning they have crossed the heliopause, the boundary where the sun's solar wind yields to the interstellar medium. Those objects are Voyager 1 and Voyager 2. Voyager 1, launched in September 1977, and now bearing the distinction of being the most distant human-made object ever constructed, is currently at approximately 172 astronomical units from the Sun, which works out to around 7 billion kilometres. It is travelling at roughly 17 kilometres per second. Those numbers sound formidable. They are, in the context of anything humans have ever built, genuinely extraordinary achievements of engineering and orbital mechanics. But 17 kilometres per second, sustained for the distance to Proxima Centauri, would require approximately 74,000 years. 74,000 years. To put that in human terms, 74,000 years ago, Homo sapiens had not yet migrated out of Africa in significant numbers. The cave paintings at Lascaux would not be made for another 40,000 years. Writing would not be invented for 68,000 years. Human civilization in its entirety represents roughly 6,000 years of accumulated culture, institution, and technology. The gap between the Earth and the nearest star, crossed at the fastest speed our best spacecraft has achieved, is 12 times longer than the whole of recorded human history. This is not a problem of engineering as it is currently constituted. This is not a problem that a slightly better rocket engine solves. This is something more fundamental, a challenge that reaches down into the deep physics of energy, mass, and the structure of space-time itself. And yet here is the extraordinary thing, the thing that makes this topic so much more than a simple catalogue of discouraging numbers. We have, in the past half-century, not only calculated the distance and registered the despair, but also seriously, rigorously, with genuine scientific credibility, begun to think about how to cross it. Engineers and physicists and dreamers of a very specific, technically literate variety have designed spacecraft. They have run the numbers on fuel, on acceleration, on shielding, on communications, on the biology of crews. Some of those designs are breathtaking in their ambition. Some of them, when examined closely, reveal layers of complication that nobody warned you about. That is what this exploration is truly about. Not merely the distance, but the cascade of problems the distance creates, each one nesting inside the last like a set of Russian dolls, until you open the smallest doll and find that the problem inside is not engineering at all, but something stranger and more profound. The Alpha Centauri system, of which Proxima Centauri is the outermost member, is a triple-star system, Alpha Centauri A and Alpha Centauri B. The 2 bright points that appear as a single star to the naked eye orbit each other at an average separation of roughly 23 astronomical units, with a period of approximately 9 years. Proxima Centauri is bound, very loosely, gravitationally speaking, to this central binary, orbiting the pair at a current distance of about 13,000 astronomical units, roughly 21 light years, with an orbital period of approximately 550,000 years. It is, in cosmological terms, barely attached. Some researchers have debated whether Proxima is truly gravitationally bound to the central pair at all, though current orbital analysis suggests that it is, albeit with an orbit so enormous that calling it a companion feels like calling Pluto a suburb of Miami. Proxima Centauri itself is a red dwarf, a small, cool, dim star with roughly 12.5% of the Sun's mass and approximately 14% of the Sun's diameter. It is so dim that it emits only about 0.17% of the Sun's luminosity, and it is completely invisible to the naked eye from Earth, despite being our nearest stellar neighbour. If you wanted to see Proxima with your unaided eye, you would need to travel to within about 4 light-years of it, which, of course, is more or less where you would need to be to visit it in the first place. It is a small, dim, orange-red ember of a star, burning slowly and miserly, fusing hydrogen at a rate so conservative that astronomers estimate it will continue to do so for approximately 4 trillion years, more than 290 times the current age of the universe. Red dwarfs are the most common type of star in the Milky Way galaxy. Roughly 70% of all stars are red dwarfs. Our galaxy contains somewhere between 200 and 400 billion stars in total, which means that perhaps 140 to 280 billion of them are red dwarfs. By the numbers alone, red dwarfs are what the cosmos is predominantly made of, and Proxima is in a sense a representative specimen of the galaxy's dominant stellar type, small, slow-burning and very, very long-lived. In 2016, a team of astronomers led by Guillaume Anglada-Escudé at Queen Mary University of London announced something that made every space enthusiast on Earth sit a little straighter. Using data from the high-accuracy radial velocity planet searcher, the HARP spectrograph at the European Southern Observatory in Chile, and combining it with older archival data from nearly a decade of careful, patient observation, they announced the discovery of a planet orbiting Proxima Centauri, a world roughly 1.3 times the mass of Earth, sitting in the habitable zone of its star, that Goldilocks band of orbital distance where liquid water can theoretically exist on a planetary surface. It was named Proxima Centauri b, and suddenly the nearest star was not merely the nearest star, it was potentially the site of the nearest world, the nearest other world, orbiting the nearest other star at 4.2465 light-years. And this changes everything about how we think about the distance problem, because the question is no longer purely abstract. It is no longer simply a matter of intellectual exercise in physics and engineering. There is, potentially, something there. There may be a planet, warm enough, massive enough, positioned correctly enough, that a probe or a crew or a signal could one day reach and find something remarkable. The distance has a destination, which is exactly when the complication begins. In 1973, a group of 11 engineers and scientists gathered under the auspices of the British Interplanetary Society and began what would become one of the most rigorous and sobering exercises in speculative spacecraft design ever undertaken. They called it Project Daedalus, after the mythological craftsman who built wings of wax and feathers, a choice of name that, with hindsight, carries an uncomfortable amount of foreshadowing. Their goal was straightforward: design in as much engineering detail as possible an unmanned probe capable of reaching another star within 50 years of flight time. They had access to the physics of 1973. They could invoke future technologies, but those technologies had to be grounded in real physical principles. No hand-waving, no undefined breakthroughs. The design had to be internally consistent, thermodynamically honest, and mathematically coherent. 50 years of work produced a design that weighed, at launch, approximately 54,000 tons, was propelled by a pulse fusion engine igniting 250 pellets of deuterium and helium-3 fuel per second, and would accelerate to approximately 12% of the speed of light, before coasting the remainder of the journey. 12% of the speed of light. At that velocity, the trip to the Proxima Centauri region would take approximately 36 years of flight time. Not 74,000 years, 36 years, a human lifetime, the kind of timeline a person can actually comprehend, can hold in their hands, can relate to the span between their own birth and their first grey hairs. And when you read the Daedalus report, there is a quality to it, a density of footnotes, a precision of specification, a relentlessness in the accounting, that feels genuinely different from science fiction. These were not dreamers idly sketching impossible machines. They were engineers confronting a real problem with real tools, and the design that emerged, for all its extraordinary ambition, violated no known physical law. It was, and remains, a serious document. But then you look at the numbers a second time. 54,000 tons of spacecraft at launch. For comparison, the Saturn V rocket that sent Apollo astronauts to the Moon weighed roughly 2,970 tons on the launch pad, fully loaded with propellant, crew module, landers, the whole apparatus. Daedalus, in its initial configuration, would mass approximately 18 Saturn VS, and the fuel alone, the deuterium and helium-3 required to drive this machine to 12% of light speed, would mass approximately 46,000 tons, leaving about 800 tons for the actual spacecraft structure and scientific payload. The Saturn V, remember, lifted 130 tons to low Earth orbit, getting 54,000 tons anywhere near a viable launch trajectory would require an entirely different class of engineering. Not an improvement on existing rockets, but a wholesale departure from chemical propulsion as the primary means of getting mass off Earth. And then there is the helium-3. Helium-3 is a stable isotope of helium, rare on Earth to the point of near non-existence, but believed to exist in significantly larger quantities on the Moon, deposited over billions of years by the solar wind. The Daedalus proposal acknowledged this and suggested mining the Jovian atmosphere as a source of the required helium-3 in sufficient quantities. The total mass of helium-3 required for the mission was estimated at around 30 tons, which would require mining Jupiter's atmosphere on an industrial scale for approximately 20 years. Not an impossible technology, but a technology that does not currently exist, that requires orbital infrastructure that does not currently exist, and that demands an energy investment before the journey even begins that dwarfs everything humanity has ever collectively attempted in the field of space exploration. This is what I find genuinely vertiginous about the Daedalus problem. Not that it is impossible in principle, but that the prerequisites are so vast, so architecturally demanding of a civilization that has not yet assembled even the first layer of the infrastructure required. The mission, considered in isolation, looks audacious. Considered in its full context, the mining, the transport, the assembly, the launch infrastructure, the communication network, the scientific community that would need to sustain interest and funding across multiple human generations. It is not one project. It is a civilization-level commitment. It is the space program, not as Apollo was the space program, a geopolitical sprint lasting 12 years, but as a permanent, multi-generational, deep-pocketed endeavour spanning at minimum 50 years of mission flight time, preceded by perhaps a century of preparation. Daedalus was ultimately a thought experiment with rigorous bones. It showed that the physics was not prohibitive. It also showed that the physics, in demanding what it demanded, had effectively raised the bar to a height no existing institution could clear, and Daedalus assumed a one-way journey. An unmanned probe that would fly through the target system, observe it for a period of days or weeks at a minimum closest approach distance of somewhere around 400 astronomical units, then continue into the darkness beyond, transmitting data back at the speed of light. A transmission that would itself take 4.2 years to reach Earth. No slowdown, no orbit, no landing, no return. This is the other dimension of the distance problem that does not announce itself in the headline figure of 4.2 light-years, but which reveals itself when you push hard on the engineering. Accelerating a spacecraft to a significant fraction of the speed of light is brutally difficult. Decelerating it, once it has arrived, is in many ways even harder. Deceleration requires fuel. The same principle, Newton's third law, the same brutal accounting, and fuel has mass, and mass requires more fuel to move, and the equation spirals outward with a kind of mathematical cruelty. The Tsiolkovsky rocket equation, derived in 1903 by Konstantin Tsiolkovsky, a Russian schoolteacher and visionary, who correctly anticipated many of the fundamental principles of rocket propulsion 60 years before the space age began, makes this explicit in its unforgiving structure. The rocket equation states that the velocity change achievable by a rocket depends on the ratio of its initial mass to its final mass, multiplied by the effective exhaust velocity of the propellant. The consequence of this equation, when applied to interstellar distances, is that the fuel required to decelerate at the destination balloons the total required fuel mass to a point where a round-trip mission carrying a meaningful payload becomes, by current physics, an extraordinary challenge, demanding initial fuel masses that dwarf the payload by factors that climb into the hundreds or thousands, depending on the target velocity. Project Longshot, a design study conducted by the US Naval Academy and NASA's Langley Research Center in the late 1980s, arrived at similar conclusions through a different technical approach, nuclear pulse propulsion, and produced a design of similar ambition and similar prerequisite burden. 100 years of flight time to reach Alpha Centauri, with a mass at launch of roughly 400 tons, no crew, no deceleration. One way again, all of the serious engineering proposals for interstellar travel share this family resemblance. They are unmanned, they are one way, and the smallest of them still require energy sources and launch infrastructures that make the entire history of human spaceflight look like a rehearsal. So the question that has begun accumulating in the background of all this engineering analysis, the question that has not yet been formally posed, but which the numbers keep gesturing toward, is this: is the distance actually the problem? Or is the distance merely the symptom of a deeper problem? A problem not in physics, but in scale, in time, and in the very nature of what it means for a biological species, evolved for a single planet, to attempt to reach another star. There is a moment in the career of almost every engineer who has seriously studied interstellar propulsion when the same thought arrives, wearing a deceptive clarity. What if we make the spacecraft smaller? What if, instead of a 54,000-ton fusion behemoth, we built something the size of a smartphone, a gram-scale probe, a wafer of sensors and transmitters, so light that the fuel equation changes entirely? This is the seed of breakthrough Starshot, and it is, on its face, one of the most genuinely creative responses to the Tsiolkovsky trap that the 21st century has produced, announced in April 2016. The same year, remarkably, as the discovery of Proxima b, Breakthrough Starshot was a $100 million research program funded principally by the technology entrepreneur Yuri Milner and backed by, among others, the late Stephen Hawking. The concept dispensed with onboard fuel almost entirely. Instead of carrying the energy source on the spacecraft, the energy would be delivered from Earth by a ground-based array of lasers, generating a combined power output of approximately 100 gigawatts. For comparison, this is roughly the total electrical generating capacity of all of Germany. Focused onto a reflective light sail of a few square meters attached to a gram-scale nanocraft, containing miniaturized cameras, communication equipment, and navigation systems. The laser pulse would last only a matter of minutes, but during that time the nanocraft would accelerate to approximately 20% of the speed of light. At 20% of light speed, the journey to Proxima Centauri would take approximately 20 to 25 years. Combined with the 4.2-year communication delay for signals to return to Earth, scientists alive at the time of launch could, in theory, receive the first data from the Proxima system before the end of their careers. This is not a generation ship. This is not a 100-year mission. This is a conceivable project on a human timescale within the span of a working scientific life, and the physics, in its broadest strokes, does not forbid it. Photon pressure, the tiny but real force exerted by light on a reflective surface, is a real phenomenon measurable in laboratories today. The Japan Aerospace Exploration Agency's IKARO spacecraft demonstrated solar sail propulsion in 2010, measuring photon pressure directly as a propulsion mechanism. The principle is sound, but then you push on the engineering. The laser array required is 100 gigawatts. For context, a typical nuclear power plant generates about 1 gigawatt of electrical output. The Starshot array would require the equivalent of 100 such power plants, generating their full output simultaneously and combining it into a single coherent, tightly focused beam. This is not merely an engineering challenge at the level of building a large laser. This is a challenge of beam coherence, keeping 100 gigawatts of laser power organized, phase-locked, and pointing at a sail that is already moving at tens of kilometers per second within seconds of the pulse beginning, and doing so without the beam diverging catastrophically, or the multiple laser elements drifting even fractionally out of alignment. The beam diffraction alone presents a problem of extraordinary precision. A laser beam, no matter how well collimated, spreads as it travels. The degree of spreading is determined by the ratio of the beam's wavelength to the diameter of the aperture producing it. To keep a 100 gigawatt beam focused on a sail of a few square meters during the entire acceleration phase, which occurs close to Earth, so the geometry is more forgiving, requires a phased array with aperture dimensions measured in kilometers, aligned to tolerances measured in nanometers, operated in atmospheric conditions that introduce fluctuating phase distortions from wind, temperature gradients, and humidity variations. Adaptive optics systems exist that can partially correct for atmospheric distortion, but at 100 gigawatts of laser power, the atmosphere above the array would itself be heated and ionized by the beam, creating a dynamic, turbulent column of changed air that the correction systems would need to continually compensate for. This is not science fiction. These are real engineering problems of real and extraordinary difficulty that the Breakthrough Starshot team has openly acknowledged. The initiative has published its technical challenges on its own website. The list includes thermal management of the sail under 100 gigawatts of illumination, the structural integrity of a sail that must both be light enough to be driven by photon pressure and robust enough to survive the acceleration loads, the pointing and tracking requirements for the laser array, and the development of miniaturized instruments capable of returning scientifically useful data across 4.2 light-years of interstellar space on the power budget of a gram-scale battery. But there is a problem that the Tsiolkovsky trap introduces in a new form for Breakthrough Starshot, and it is one that does not appear in the list of engineering challenges. It is a physics problem, and it is this: at 20% of the speed of light, the interstellar medium is no longer background noise. It is a wall, the interstellar medium, the tenuous fog of gas and dust that fills the space between stars, is by ordinary standards almost nothing. The density of the interstellar medium in the local neighbourhood of the Sun is approximately 1 hydrogen atom per cubic centimetre. This is far better vacuum than anything achievable in any laboratory on Earth. By any human measure, interstellar space is empty. But a spacecraft travelling at 20% of light speed encounters approximately 60,000 kilometres of interstellar medium every second. At that velocity, each hydrogen atom struck by the spacecraft carries a kinetic energy in the spacecraft's reference frame, equivalent to a very energetic particle of the kind produced by cosmic ray showers. And it is not just hydrogen atoms. The interstellar medium contains dust grains, particles of silicate and carbonaceous material, ranging from tens of nanometers to a fraction of a millimeter in size. At 20% of the speed of light, a single dust grain with a mass of 1 microgram, 1/1,000,000th of a gram, invisible to any naked eye, impacts the sail with kinetic energy roughly equivalent to a rifle bullet. Over the course of a 20-year journey, traversing some 4 light-years of interstellar medium at this velocity, the accumulated impact flux is not trivial. Calculations suggest that the leading surface of the sail would be eroded, pitted, and potentially destroyed by dust collisions before reaching the halfway point of the journey. Several strategies have been proposed, orienting the sail edge-on during the coast phase after the laser acceleration is complete, using a beryllium-copper alloy or other ultra-hard material for the leading edge, or protecting the payload with a small beryllium shield a few millimeters thick. Each strategy works partially. None works completely. Each adds mass, and mass is the enemy. And then there is the radiation. The interstellar medium contains galactic cosmic rays, high-energy protons and heavier nuclei, accelerated to near-light speed by supernova remnants and other violent astrophysical processes, streaming through the galaxy at essentially all times. For humans on Earth's surface, The atmosphere and magnetosphere provide shielding that reduces cosmic ray exposure to manageable levels. In the interstellar medium, at relativistic speeds, a gram-scale nanocraft has no shielding worthy of the name. The cumulative radiation damage to onboard electronics over a 20-year cruise phase is an unsolved problem. Radiation hardening of electronic components exists as a technology developed primarily for satellites in high Earth orbit, but the cosmic ray environment in the interstellar medium is more intense and more energetically diverse than anything a satellite encounters in Earth's vicinity, and the exposure time is orders of magnitude longer. What I find so instructive about the breakthrough starshot scenario, and I want to be precise here, because starshot represents the best current thinking from some of the world's most capable engineers and physicists, is that it demonstrates a fundamental principle about the distance to Proxima Centauri. Every attempt to reduce the journey time creates a new and proportionally severe set of problems. Slow spacecraft avoid the dust and radiation problem, but are imprisoned by the fuel and time problem. Fast spacecraft escape the fuel problem, but are ambushed by the dust and radiation problem. Making the spacecraft smaller solves the mass problem, but multiplies the precision and miniaturization problems. Removing onboard fuel solves the Tsiolkovsky trap, but creates the atmospheric correction and beam coherence problems. The distance to Proxima Centauri is, in this sense, a problem that does not have a single throat to be seized. It has multiple throats, and seizing any one of them leaves the others intact. This is not, I want to emphasize, a reason for despair. It is, in fact, a deeply honest description of where science and engineering currently stand. And honest descriptions are the only kind worth having. The problems are real, they are specific, they are measurable. And specific, measurable problems are the kind that engineering can eventually solve, given sufficient time, sufficient resources, and sufficient ingenuity. The history of science is substantially a record of problems that appeared insurmountable until the moment they were surmounted. But there is another layer to this cascade of complications, a layer that the engineering community has been slower to confront directly, because it does not sit comfortably in a technical specification or a materials science paper. It is the question of what, exactly, waits at the other end of the journey, because Proxima Centauri b, the potential world in the habitable zone, the planet that gave the whole question its emotional and scientific urgency. Proxima b is not simply the nearest Earth. It may, in fact, be one of the most hostile environments in the known galaxy. When Anglada Escudet's team published their discovery paper in the journal Nature in August 2016, the response was, to put it plainly, electric. Within 24 hours, the story had penetrated every major news outlet on the planet. Earth-like planet found orbiting nearest star, the headlines declared. Scientists find potentially habitable world next door. The language of possibility cascaded outward into the broader culture with a speed that outpaced the scientific caveats considerably. And the scientific caveats were considerable. Let us begin with what Anglada Escudet's team actually measured. The technique they used, radial velocity, also called the Doppler method, works by detecting the tiny wobble that an orbiting planet induces in its host star. When a planet orbits a star, the gravitational pull of the planet causes the star to move slightly toward and away from us as the planet traces its orbit, and this movement shows up as a tiny Doppler shift in the star's spectrum, a slight blue shift as the star approaches, a slight red shift as it recedes. By measuring this shift with extraordinary precision, astronomers can determine the orbital period of the planet and calculate a minimum mass. The minimum mass of Proxima b, derived from these measurements, is approximately 1.17 Earth masses, with an orbital period of 11.2 days. Given its orbital distance from Proxima Centauri, roughly 0.0485 astronomical units, approximately 7.2 million kilometers, it sits within what astronomers calculate as the habitable zone for a star of Proxima's luminosity. In other words, a planet at that distance from Proxima would receive enough stellar energy to theoretically maintain liquid water on its surface, if conditions were right. Those 3 words, "if conditions were right," are doing a very great deal of work in that sentence. Proxima Centauri is, by the measure of stellar aggression, one of the more hostile stars in the solar neighbourhood. It is what astronomers classify as a flare star, a class of red dwarf characterised by violent, unpredictable eruptions of energy that dwarf in proportion anything produced by the Sun during its worst storms. The Sun occasionally generates solar flares, events in which a burst of electromagnetic radiation and charged particles is released from the solar surface following a rapid magnetic reconnection event. Major solar flares, classified as X-class events, are powerful enough to disrupt satellite communications, damage unprotected spacecraft electronics, and produce auroras visible at mid-latitudes on Earth. Proxima Centauri produces flares of this character routinely, not occasionally, routinely. Observations by the ALMA radio telescope array in 2018 recorded a flare from Proxima Centauri that released energy at millimeter wavelengths roughly 10 times greater than any solar flare ever recorded from our own Sun. The same event, observed across multiple wavelengths, showed emission increases of factors of several thousand in ultraviolet over a timescale of a few seconds. And this was not an anomalous event. It was representative of Proxima's regular behaviour. The star emits X-ray radiation at a level roughly 500 times higher than the Sun, and during major flares, that emission can spike by a factor of 50,000. Proxima b, orbiting at 0.0485 astronomical units, receives this radiation at point-blank range. For comparison, the Earth orbits the Sun at 1 astronomical units. The distance from Earth to the Sun is 20 times greater than the distance from Proxima b to Proxima Centauri. And because radiation intensity falls off with the square of distance, Proxima b is, at baseline, bombarded by approximately 400 times more high-energy radiation than Earth, even before accounting for flares. During a major flare event, the numbers become, in the most literal scientific sense, extraordinary. The question this raises, and it is the central question around which the habitability debate orbits, is whether Proxima b has an atmosphere. Because an atmosphere, in the right configuration, can accomplish many remarkable things. It can scatter and absorb ultraviolet radiation before it reaches the surface. It can redistribute heat from the day side to the night side. It can maintain pressure sufficient to keep liquid water stable. And it can provide a globally accessible chemical environment in which the kind of chemistry associated with life can proceed. Without an atmosphere, the surface of Proxima b is directly exposed to the full force of Proxima Centauri's radiation environment. With one, a great deal becomes possible, but the very factors that make an atmosphere necessary are also the primary mechanisms by which an atmosphere is removed. Stellar wind, the continuous stream of charged particles shed by a star's corona, has the capacity to erode a planetary atmosphere by transferring momentum to atmospheric molecules, lifting them above the escape velocity of the planet and carrying them away into space. For Earth, the Sun's stellar wind is deflected primarily by the planet's magnetic field, which creates a protective bubble, the magnetosphere, that channels most of the stellar wind around the planet rather than into it. This is why Earth retains its atmosphere after 4.5 billion years of solar wind exposure. But the stellar wind from Proxima Centauri is not comparable to the solar wind Earth experiences. Studies have estimated that the stellar wind particle flux striking Proxima b is between 4 and 80 times higher than the solar wind flux at Earth, combined with the ultraviolet and X-ray radiation bombardment, which photoionizes the upper atmosphere, allowing particles to escape more easily. This creates an environment that atmospheric models suggest is extremely hostile to long-term atmospheric retention. This is what researchers have called the Proxima atmospheric loss problem, and it is more severe than the equivalent problem for most planets in the habitable zones of Sun-like stars, for a reason that is deeply embedded in orbital mechanics. Proxima b, at an orbital distance of 0.0485 astronomical units, orbits its star once every 11.2 days. At this distance, tidal forces from Proxima Centauri are expected to have locked the planet's rotation to its orbit, meaning one hemisphere always faces the star perpetually bathed in its light, while the other faces permanent darkness. This tidal locking is a consequence of the same physics that keeps one face of our moon always pointing toward Earth. Over time, gravitational gradients synchronize rotation and orbital period. For a planet as close to its star as Proxima b is to Proxima, the timescale for tidal locking is estimated at a few 100 million years, short compared to the age of the system. Tidal locking does not automatically preclude habitability. Some atmospheric circulation models suggest that a sufficiently thick atmosphere on a tidally locked planet could transport heat from the day side to the night side efficiently enough to prevent the catastrophic freezing of the night hemisphere. The so-called atmospheric collapse scenario, in which all atmospheric gases condense and freeze on the cold side, leaving the rest of the planet exposed to vacuum. But maintaining that atmosphere under a stellar wind of the intensity Proxima generates, and without the magnetic protection that a rapidly rotating, internally active planet might generate, is a problem that remains genuinely unresolved. And there is a further complication, one that sits at the intersection of magnetism, geology, and deep time. A planet generates a global magnetic field through a process called the geodynamo, convective motion of conducting material in its liquid outer core, driven by both heat from radioactive decay in the core and the heat released as the iron-nickel core gradually solidifies from the inside out. Earth's geodynamo has been operating for at least 3.5 billion years, and probably longer, and its field strength is sufficient to deflect the solar wind with reasonable efficiency. But Proxima b is not Earth. It may be larger, and it occupies a very different thermal environment. Models of its interior suggest that if the planet formed with an Earth-like composition, it could conceivably maintain a geodynamo. But the conditions under which that dynamo would be sustained, the cooling rate, the composition, the internal heat budget, depend on the planet's formation history, which we cannot currently determine. A 2017 study found that even if Proxima b has a strong magnetic field, the combination of stellar wind pressure and radiation would still result in significant atmospheric loss on geological timescales. The magnetic shield buys time. It does not guarantee retention. The picture that emerges when all of these constraints are assembled honestly is of a planet that could be habitable under very specific, somewhat optimistic conditions: a sufficiently thick atmosphere, a strong magnetic field, a formation history that provided abundant volatile materials to replenish what the stellar wind stripped away, but which could equally be a barren, airless rock, scoured by radiation and blasted by stellar flares to a state of such thorough hostility that the phrase habitable zone would ring as black comedy. We do not currently know which of these pictures is correct. Here is what makes this fact both scientifically honest and, to my mind, one of the most profound sources of tension in all of contemporary astronomy. The James Webb Space Telescope, our most powerful observatory, was not designed primarily for this task. Characterizing the atmosphere of a planet around a red dwarf at 4.2 light-years, a planet detected only through the radial velocity wobble it induces in its star, with no confirmed direct detection via the transit method, is at the extreme edge of what any current instrument can do. Webb has attempted transit observations of Proxima b, but the geometry is uncertain. Whether the planet actually transits the disk of its star as seen from Earth has not been confirmed, and without a confirmed transit, direct atmospheric spectroscopy is essentially impossible with current technology. So the nearest potential world in the habitable zone of the nearest star remains, in 2026, a shape seen only in the wobble of a star's spectrum, a gravitational whisper, a mathematical inference, a mass in a zone where water could exist. If the conditions are right, the distance to Proxima Centauri is 2,465 light-years. The distance to certainty about what waits there is considerably further. In the summer of 2013, Guillaume Anglada Escudé was a relatively young astronomer, working in obscurity by the standards of his field, piecing together a scientific case that almost nobody else was willing to make. He had obtained a position at Queen Mary University of London after postdoctoral work at the Carnegie Institution and the University of Göttingen, and he had been developing a speciality in radial velocity precision. The painstaking, unflashy work of extracting minute Doppler signals from stellar spectra with the highest possible accuracy. It is work that requires not just technical skill, but a particular temperament. The patience to work with numbers that are almost indistinguishable from noise, the discipline to maintain rigorous skepticism about your own results, and the will to keep looking after months of finding nothing. Radial velocity as a planet detection method is inherently imprecise in a way that is easy to underappreciate from the outside. The Doppler wobble induced in a star by an Earth-mass planet in a short orbital period is a velocity shift of roughly half a metre per second, a comfortable walking pace. The spectrographs used to detect this shift are instruments of extraordinary refinement. HARPS, the high-accuracy radial velocity planet searcher at the European Southern Observatory in La Silla, Chile, is capable of measuring stellar velocity changes of approximately 0.97 meters per second. This is among the best precision achievable with any instrument currently operational. It means that HARPS can, in principle, detect the signal of a planet like Proxima b, but only after many observations carefully combined with meticulous corrections for instrumental drift, atmospheric dispersion, and the intrinsic noise of stellar surface activity. That last factor, stellar activity, was the core of Anglada Escudet's problem. Proxima Centauri is an active star. Its surface is restless, churning with convective cells and magnetic field lines that produce spots, plage, flares, and a continual low-level variability in its spectral signature. This intrinsic stellar noise masquerades as a Doppler wobble. In the jargon of the field, it is called the stellar activity signal, and it can be larger than the planetary signal you are trying to detect. Disentangling a genuine planet signal from stellar activity is less like finding a needle in a haystack, and more like finding a very thin needle in a haystack made entirely of slightly thicker needles. The methods used to perform this disentanglement are mathematical, statistical, and deeply contested within the community. Different researchers applying different modelling approaches to the same dataset can arrive at different conclusions about whether a planetary signal is real or an activity artifact. Anglada Escudet had been aware of hints of a potential signal in Proxima's radial velocity record for years before 2016. Earlier analyses of archival data from the UV spectrograph at the VLT in Chile, dating back to 2000-2001, showed a periodicity in the radial velocity residuals at approximately 11.2 days. But the statistical significance was marginal, and the dataset was too sparse to rule out stellar activity as the explanation. The signal was there, possibly, or it wasn't. The data couldn't decide. What Anglada Escudet did in 2015 and 2016 was mount a dedicated observational campaign. He called it the Pale Red Dot campaign, a deliberate echo of Carl Sagan's Pale Blue Dot, the famous photograph of Earth taken by Voyager 1 from a distance of 6.4 billion kilometers, which Sagan used as the basis for one of the most searching meditations on human smallness and fragility in the literature of science. Anglada Escudet's campaign solicited 60 hours of HARPS observations across a period of 3 months, supplemented with photometric monitoring to track Proxima's brightness and characterize its activity variations simultaneously. The goal was to generate enough simultaneous data, spectroscopic and photometric, Doppler and direct brightness, to allow the stellar activity signal and any planetary signal to be disentangled with statistical confidence. The observing campaign ran from January to April 2016. Anglada Escudet conducted it with a team of 31 co-authors from institutions across Europe, Chile, the United States, and Australia. A collaboration assembled over years of informal conversations, conference hallway discussions, and email chains, the kind of social scaffolding that holds modern big science collaborations together. The data came in nightly, processed and checked by observers in Chile, who then transmitted it to the team for analysis. The atmosphere of the campaign was, by multiple accounts, one of sustained, disciplined excitement, the kind that scientists learn to suppress publicly because extraordinary claims require extraordinary evidence, but which is privately almost impossible to contain. When the final analysis was run, when the stellar activity model was subtracted, and the residual signal examined, the planetary signal at 11.2 days was there. Its amplitude corresponded to a minimum planet mass of 1, 17 Earth masses, with a statistical confidence level high enough to satisfy the standard thresholds for a discovery claim. The planet was real, or at least as real as anything detected by the radial velocity method could be declared to be. The pale red dot team went quiet for 3 months, while the paper went through peer review at Nature. This is standard practice in science, and it is also one of the most psychologically demanding periods in a scientist's professional life. The knowledge sits inside you, burning, while the editorial process grinds forward. Anglada Escude had, in effect, found the nearest otherworld known to science. He had done it with patience, with technical rigour, and with a refusal to be discouraged by earlier ambiguous data. He had spent years on a signal that most of his community was not actively pursuing, precisely because the stellar activity of Proxima Centauri made the problem seem intractable. And then there is the detail that I find most human about this story, most unexpectedly moving. Anglada Escude ran the Pale Red Dot campaign as an open science project. Daily updates were posted to a public website. Blogs, graphs, photographs from the observatory, explanations of the methodology written for non-specialist audiences. The observing team documented their work in real time, openly, while they were doing it. This was, in 2016, an unusual choice. Open science practice is gaining traction in the research community, but in astronomy, a field with intensely competitive prioritization of discovery credit, conducting a live public broadcast of an ongoing search for the nearest exoplanet was a conspicuous act of scientific generosity. It was also, as Anglada Escude later reflected in interviews, a calculated choice. The open documentation created a public record that removed any ambiguity about the timeline and process of the discovery. The paper was published in Nature on the 24th August 2016. The title was direct, almost blandly so: a terrestrial candidate planet in the temperate zone of Proxima Centauri. It generated 1-200 media stories in its first 48 hours. Anglada Escude gave interviews in Spanish, English and Catalan. He was careful in all of them to distinguish between what the data showed, a minimum mass planet in the habitable zone, and what it did not show, anything about its atmosphere, its surface, its geology, or its prospects for harbouring life. But the emotional weight of the discovery was not really containable within scientific caveats, and Anglada Escude himself did not try too hard to contain it. "This is the most important exoplanet we have found," he said in one interview. "It is the nearest. If we can characterize it, and if we can one day reach it, then this is where the story of humanity's expansion into the cosmos might begin." There is something worth pausing over in the phrase, "if we can one day reach it," because Anglada Escude was not naive about the distance. He knew, with the precision of someone who had spent years staring at light that left Proxima Centauri 4.2 years before it reached the spectrograph in the Atacama Desert, exactly how far away the planet he had found was. He had dedicated years of his career to a star that could not be seen with the naked eye. In a hemisphere most of his northern European colleagues barely considered, hunting a signal smaller than walking pace in the spectral noise of a flaring, restless dwarf star, and he had found it. And what he found was the beginning of a question, not an answer, a destination, not an arrival. The human story buried in the science of interstellar distance is not the story of a hero who solved the problem. It is the story of a generation of scientists who have made the problem precise enough to be honestly confronted, who have mapped the edges of the darkness with sufficient accuracy that the people who come after them will know exactly what they are walking toward. Anglada Escude found the planet. He did not solve the distance. He made the distance matter more. I find that in its own way as significant a contribution as the discovery itself. The Pale Red Dot campaign's legacy runs deeper than the discovery paper. It established a model for how the next generation of planet searches, with instruments of significantly greater capability, such as the extremely large telescope currently under construction in the Atacama Desert, which will have a primary mirror of 39, 3 meters in diameter, and the capacity to potentially directly image nearby exoplanets, might be conducted, not in the secrecy of competitive science, but in the open, watched by a world that has a stake in the answer. Because the world does have a stake in the answer. The question of whether Proxima b has an atmosphere, whether it is a world in any meaningful sense, or merely a rock in a calculation, is not purely an academic matter. It is, in the most direct sense possible, a question about whether the universe contains more than one home, and that brings us to the stakes, properly understood. Because what we have been discussing up to this point is the problem of getting there, the problem of propulsion, fuel, time, radiation, dust, engineering ambition, and the human capacity to sustain multi-generational projects. We have not yet fully reckoned with what it would mean for civilization, for the long-run arc of our species. If the distance to Proxima Centauri were actually crossed, what would we become as a species if we could reach the nearest star? And harder question, what might we lose in the attempt? There is an idea in strategic planning and complex systems analysis called the cost of entry, the minimum investment required before a competitive space can even be accessed. In commercial markets, cost of entry for building semiconductor fabrication plants is currently around $15 to $20 billion per facility. For launching a new commercial airline, it runs into the hundreds of millions at minimum. For building the Large Hadron Collider at CERN, the most complex scientific instrument ever constructed, the cost was approximately $9 billion over the course of its design and construction phase, sustained by a collaboration of 22 member states over roughly 20 years. The cost of entry for an interstellar mission to Proxima Centauri is, by any serious analysis, an order of magnitude beyond any of these examples. Not because the physics is exotic, but because the engineering requirements at every level of the project stack are each individually at the limit of what our civilization can currently achieve. And the stack has many levels. Let us be concrete. Breakthrough Starshot's $100 million research budget, substantial as it is, was explicitly described as sufficient only to investigate whether a laser-sail nanocraft system was feasible, not to build one, not to test one at interstellar scale, not to launch one. A full system, the Starshot team has estimated, would cost approximately $5 to $10 billion to develop and operate. The 100-gigawatt laser array would need to be sited at high altitude, in a radiatively dry environment, possibly the Atacama, possibly the Antarctic plateau, and would represent a structure of extraordinary complexity. The power supply alone, whether from a dedicated nuclear plant or a grid-scale renewable installation, would require construction timelines measured in decades and capital investments in the billions. And then there is the question of what, exactly, a gram-scale nanocraft can tell us when it arrives. At 20% of the speed of light, the transit time through the Proxima Centauri system, assuming closest approach passes within detectable range of Proxima b, would be measured in hours. During those hours, the onboard instruments would collect whatever data they could. Spectroscopic signatures from the planet's surface or atmosphere if it has one, images at whatever resolution the tiny optics of a nanocraft can achieve, measurements of the magnetic and particle environment in Proxima's immediate neighbourhood. That data would then be transmitted back at the speed of light, arriving at Earth 4.2 years later. What resolution can a nanocraft achieve? This is a question worth slowing down for, because it reveals a tension at the heart of the miniaturization strategy that Starshot represents. The resolving power of any imaging system is determined by the ratio of the wavelength of light to the diameter of the aperture. A camera lens with a diameter of 1 centimeter, imaging at visible wavelengths of roughly 500 nanometers, has a diffraction-limited angular resolution of approximately 50 microradians. At a closest approach distance from Proxima b of, let us say, 1 million kilometers, a close flyby. This corresponds to a spatial resolution on the planet's surface of roughly 50 kilometers. You could distinguish continent-scale features. You could not resolve anything at the scale of a city, let alone a biosphere signature. To do significantly better, to resolve features at say 1 kilometer resolution, you would need an aperture of roughly 50 centimeters. At that aperture, the sail is no longer gram scale, the propulsion requirements change, and the entire architecture of the Starshot concept requires revision. The miniaturization that makes Starshot's physics tractable is precisely what limits its scientific yield at the destination. This is, I want to be clear, not a fatal argument against Starshot, a flyby that returns any information at all about the Proxima system would be historically unprecedented. The first direct measurement of another stellar system, the first observation of a world other than those in our own solar system at close range. Even a blurry, low-resolution image of Proxima b, if the flyby geometry is right, would be the most consequential photograph in the history of science. The scientific value would be enormous regardless of resolution. But there is a gap, a chasm, really, between the most consequential photograph in the history of science and a definitive characterization of whether Proxima b is habitable. And bridging the chasm requires something more than a nanocraft. It requires, eventually, a probe that can slow down, that can enter orbit, that can remain in the Proxima system for months or years, making repeated observations across the full electromagnetic spectrum, potentially even descending through an atmosphere if one exists. A probe that can slow down at the destination must carry deceleration propellant, or be equipped with a deceleration mechanism, or exploit some resource at the destination, such as a powerful laser system based there, which would require a previous mission to deliver and assemble it. The Tsiolkovsky trap reasserts itself the moment deceleration enters the requirements. Every approach to this problem that has been seriously studied eventually bottoms out at the same fundamental constraint. Crossing 4 light-years and doing useful science at the other end requires an energy investment commensurate with a major civilizational commitment sustained over timescales comparable to the longest-running scientific programs in history. This is not merely an engineering problem. It is a governance problem, a cultural problem, and a temporal problem. The question is not whether our physics permits the mission. It does, in principle, under various technically feasible propulsion schemes. The question is whether our institutions, our economies, our cultural attention spans, and our political structures are capable of sustaining a commitment over the timescales required. Consider the longest-running scientific commitments humanity has sustained. The Large Hadron Collider, as mentioned, took roughly 20 years from initial conception to first collisions. CERN itself was founded in 1954 and required a political agreement between 12 European nations to establish, a feat of international cooperation that reflected the post-war moment's particular appetite for cooperative scientific projects. The Voyager missions, conceived in the late 1960s and launched in 1977, have now been operational for nearly half a century, but their longevity reflects the relatively modest ongoing resource demands of maintaining a communications link to existing spacecraft, not the demands of sustaining a development program. An interstellar mission requires a different category of commitment. The breakthrough Starshot concept, from announcement to data receipt, spans at minimum 30 years even under optimistic assumptions about development timelines. Assuming a first launch within 15 years of program announcement, a 20-year cruise phase, and a 4-year communication delay. A Daedalus-style fusion probe would span a century and a half from inception to data return. A crewed interstellar mission, under any currently conceivable propulsion scheme, would span multiple human generations. No democratic government has ever sustained an infrastructure project across multiple electoral cycles without significant political disruption. The history of large-scale science funding is littered with programs that were conceived in one political climate, slowed or cancelled in another, and restarted in a third, often with decades of lost momentum and institutional knowledge in between. The superconducting super collider, the planned American particle accelerator that would have significantly exceeded the LHC's capabilities, was cancelled by the US Congress in 1993 after $2 billion had already been spent and 22 kilometres of tunnel had been excavated. The cancellation was a budgetary and political decision made in a single legislative session that erased a project representing decades of scientific planning and billions of dollars of investment. An interstellar mission is not immune to this dynamic. It is in fact more vulnerable to it than almost any other scientific project, because the payoff, if it comes at all, arrives not during the political tenure of any administration that approved the funding, but during the tenure of governments that will be formed decades or generations after the current institutions have evolved beyond recognition. This is what I think of as the civilization stakes paradox of interstellar travel. The project that most clearly articulates the highest aspirations of our species is also the project most poorly suited to the institutional structures by which our species currently organises its large-scale activities. The ambition is civilizational in scope. The attention span required is civilizational in duration. But our civilization operates on 4-year electoral cycles, quarterly financial reporting periods, and news cycles measured in hours. The only human analogy I can find that partially bridges this gap, and it is an imperfect analogy but an illuminating one, is the medieval cathedral. The great Gothic cathedrals of Europe, Notre Dame de Paris, Chartres, Cologne, were construction projects that spanned centuries. Notre Dame was begun in 1163, and its nave was not completed until roughly 1250. It was still receiving major additions in the 14th century. Cologne Cathedral was begun in 1248 and was not completed in its current form until 1880, 632 years later. The people who laid the foundations of these buildings never saw them complete. Their children's 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 children finished what they started. What sustained these projects across centuries was not government funding or private equity or democratic mandate. It was institutional religion, an organisation with a longer temporal horizon than any secular institution, a continuity of purpose that transcended individual lifetimes, and a cultural framework in which the investment of a lifetime of labour in a project you would not live to see complete was understood as both meaningful and honourable. I am not suggesting that interstellar travel requires a religious framework. What I am suggesting is that crossing the distance to Proxima Centauri may require a kind of institutional infrastructure, a continuity of purpose across human generations that our current secular, democratic, quarterly earning civilization is not well equipped to provide, and the creation of that infrastructure may be as difficult, as genuinely original a human achievement as the engineering itself. This is the civilization problem of interstellar distance, and it is not solved by better rockets. It is solved by better institutions, or perhaps by a crisis so severe that it forces the question of our species' long-term future onto the political agenda with sufficient urgency and clarity that a true civilizational commitment becomes possible, which raises the question of what that crisis might be. Because there is a long-view argument for interstellar exploration that has nothing to do with scientific curiosity and everything to do with species survival. An argument that, if taken seriously, frames the distance to Proxima Centauri not as a barrier to exploration, but as the minimum required clearance for the continued existence of humanity. In 2018, a paper appeared in the journal Acta Astronautica that was unusual in the literature of spaceflight in several respects. Its title was How to Build a Crew of Generation Ships: The Genetic Population Requirements for Interstellar Travel. Its author was a researcher named Frédéric Marin, an astrophysicist at the University of Strasbourg, and it addressed with mathematical rigour a question that previous discussions of generation ship travel had tended to handle with narrative hand-waving. How many people do you need on an interstellar voyage to maintain a genetically viable, psychologically stable, socially functional population? across the multiple generations that the journey would require. Marin's analysis used a software system called Heritage, a Monte Carlo simulation designed to model human population dynamics in a closed, isolated environment over very long timescales. He ran thousands of simulations under varying initial conditions, modeling births, deaths, genetic drift, inbreeding depression, and the random events that populate any realistic model of a small, isolated community. His conclusion: a minimum founding population of approximately 98 individuals, selecting for genetic diversity and maintaining specific reproductive norms across the journey, could theoretically sustain a viable population over a 500-year voyage. That number, 98, is simultaneously reassuring and horrifying, depending on how you hold it. It is reassuring because it is not, in principle, an impossible number of people to carry. A submarine crew can number in the hundreds. A remote research station in Antarctica typically houses between 20 and 100 people during winter over. The crew complement of a nuclear aircraft carrier can exceed 5,000 people. 98 individuals is a number that sits well within the range of human communities that have existed in isolation under challenging conditions. It is horrifying for every other reason. Consider what 98 people across 5 centuries actually means. Those 98 founding crew members would, on average, produce children who grow up knowing nothing but the ship. Their grandchildren would have no memory of Earth, not even childhood memories, but no cultural memory of any kind, except what was transmitted through stories, records, and institutional knowledge maintained on the vessel. By the 5th generation, perhaps 150 years into the voyage, the concept of Earth would be to the inhabitants of the generation ship roughly what ancient Mesopotamia is to us today, a historical location, the origin of their civilization, reachable only through archives and imagination. By the 15th generation, at roughly year 450 of the voyage, the generations born on the ship would have no living connection to the culture that launched the mission. The languages, the music, the political ideologies, the social norms, the scientific paradigms that motivated the original voyage, all of these would have been filtered through 15 successive generations of transmission, each generation adapting, editing, and transforming the inheritance they received. The mission, conceived and launched by one civilization, would arrive, if it arrived, delivered by a civilization that no longer shared the original's defining characteristics, except in the most abstract genetic and archival sense. And then consider the psychology. Marin's genetic model addresses the biology. It says nothing about the sociology of a closed community sustained across centuries of deep isolation. But the sociology is, I would argue, the harder problem, because it is not constrained by mathematics in the same tractable way as genetic drift. Closed communities under extreme isolation have been studied extensively. Polar expeditions, submarines, space stations, prisons, monasteries, Antarctic research stations. The patterns that emerge are consistent and well documented. Hierarchies form and solidify. Grievances accumulate and, lacking the normal social release valves of a larger, more diverse society, they fester. The proportion of the community's cognitive and social energy devoted to internal conflict typically grows over time in closed systems, even when the external conditions are stable. On a generation ship, the external conditions are not stable. The void outside the hull is lethal to an extraordinary degree. The ship itself, no matter how carefully engineered, is a finite system that will require continuous maintenance, and maintenance tasks in an isolated community become politically contested resources. Who decides which systems get priority? Who acquires the skills to maintain critical infrastructure? How do you enforce maintenance discipline across generation boundaries when the founding crew members who understood the design implications are all dead? A ship that is 200 years into a 500-year voyage is navigated by people whose great-great-great-grandparents built and launched it, and who are maintaining systems whose original design philosophy may be documented, but whose daily operational reality is now encoded in institutional knowledge. held by people who may or may not have transmitted it fully to their successors. NASA's Human Research Program has identified long-duration mission isolation as one of the 5 top health and performance risks for deep space astronauts, alongside radiation exposure, physiological deconditioning, sensory-motor adaptation, and human-machine interaction challenges. These studies are based on missions measured in months. The International Space Station record for a single continuous stay is currently held by Oleg Kononenko at 374 days. Extrapolating the psychological and social dynamics of a 374-day mission to a 500-year voyage is not merely a quantitative extrapolation. It is a qualitative leap into territory for which we have no data, no models with real empirical grounding, and no historical precedents other than the partial and imperfect analogies of isolated communities on Earth. The generation ship is, in this sense, simultaneously the most human and the most inhumane solution to the distance problem. Most human because it leverages the one technology that humanity has perfected over millions of years, reproduction, as its primary means of sustaining the mission across time. Most inhumane because every person born on the ship after the first generation is born into a situation they did not choose. The mission's passenger rather than its crew, a citizen of a society built for a purpose older than their own birth, with a destination they cannot reach in their lifetime, and an origin they have never seen. There is a philosophical problem embedded here that has been named, in the bioethics literature, the non-identity problem, and it was articulated most rigorously by the philosopher Derek Parfit in his 1984 book Reasons and Persons. The non-identity problem asks, can we wrong people who would not exist but for the decisions we make? The children born on a generation ship would not exist had the mission not been launched. Their existence is constitutively dependent on the decision to embark. In what sense can they be said to have been wronged by a mission they have no option to leave? In what sense are they morally victims of the distance problem, rather than simply its latest inheritors? There is no clean resolution to this question, and the ethicists have argued over it for decades without convergence. But it illustrates something important about the full weight of the distance to Proxima Centauri. It is not only a physical barrier, it is a moral barrier. It forces us to confront questions about the rights of people not yet born, the continuity of collective purpose across generations, and the ethics of creating a human community whose entire purpose is defined by a journey its members did not choose and cannot complete. Now let us pivot, because the generation ship is one end of the spectrum. The other end, the end that avoids the generational ethics problem by making the journey fast enough to be completed within a single human lifetime, returns us to the physics problems. And here is where the complications multiply in ways that are, I think, not sufficiently appreciated in popular treatments of the subject. At significant fractions of the speed of light, the universe stops behaving in the way that our everyday intuitions suggest. Special relativity, Einstein's 1905 theory of the relationship between space, time, and motion, predicts a set of phenomena that are counterintuitive in the extreme, and that have been verified with extraordinary precision in particle accelerators, atomic clocks on satellites, and high-energy astrophysics. Among these phenomena, the most directly relevant to interstellar travel is time dilation. Time dilation is the slowing of time for a moving observer relative to a stationary one. It is not a hypothetical. It is measured routinely in the GPS satellite network, where the slight difference in clock rates between satellites in orbit and receivers on the ground must be corrected for in the navigation algorithms. Failing to do so would cause GPS accuracy to drift by roughly 10 kilometers per day. At the velocities of GPS satellites, the effect is a few microseconds per day. At velocities approaching the speed of light, the effect becomes dramatic. For a spacecraft travelling at 90% of the speed of light, time aboard the spacecraft passes at approximately 44% of the rate experienced by an observer on Earth. A journey to Proxima Centauri at 0.9c takes, in Earth's reference frame, approximately 4.7 years. In the ship's reference frame, the crew experiences approximately 2.1 years. At 99% of light speed, the dilation factor is approximately 7. The 4.3-year Earth frame journey becomes a 7-month ship time experience. At 99.9% of light speed, the factor approaches 22. The crew experiences the journey in roughly 70 days, while over 4 years pass on Earth. The asymmetry of time dilation is, on reflection, one of the genuinely strangest verified facts in all of physics. A crew that departs Earth at 99.9% of light speed makes a direct transit to Proxima Centauri, decelerates, performs a brief survey, reaccelerates, and returns to Earth would experience a round trip of perhaps a few years of ship time, while more than 8 years pass on Earth. The crew returns younger than they should be, relative to everyone they left behind, not metaphorically younger. Physically, biologically, measurably younger, by the same mechanism that keeps GPS clocks running at a slightly different rate than earthbound clocks. This is not a complication. It is a feature if you are a crew member who values your own time. It is a complication if you are trying to maintain meaningful connection between the crew and the civilization that launched the mission. In the most extreme relativistic scenarios, the crew of a fast interstellar mission could return to an Earth that is decades or centuries ahead of the one they left. A world in which everyone they knew is dead, in which the political, cultural, and technological landscape has transformed beyond recognition. The mission that was launched as an expression of civilizational aspiration returns to find the civilization has moved on. And here is the thing about 90% of light speed, or 99%, or 99.9%. The energetics are not merely challenging, they are, with current or foreseeable technology, fantastically prohibitive. To accelerate a crewed spacecraft of, say, 1,000 tons, a mass comparable to the ISS, which is about 420 tons, so roughly twice that, to 10% of the speed of light and then decelerate it at the destination requires, by the rocket equation for a fusion drive with high specific impulse, a fuel-to-payload mass ratio on the order of hundreds. To reach 90% of light speed and decelerate, the ratio becomes astronomical in every sense. The energy required to accelerate a 1,000-ton payload to 90% of light speed is approximately equal to the total energy output of the Sun over roughly 30 seconds. This is not a figure that admits of easy dismissal. The Sun produces approximately 3.8 times 10 quadphies watts. 30 seconds of solar output is about 1.14 times 10 quadphies joules. Humanity's current total annual energy consumption is roughly 5 times 10 quadjoules. The energy needed to send a crewed spacecraft to Proxima Centauri at relativistic speed, by this rough estimate, is approximately 10 million times the total annual energy output of our entire civilization. There is a propulsion concept that bypasses this fuel problem in the most audacious way imaginable. The Bussard ramjet, proposed in 1960 by physicist Robert Bussard. Rather than carrying its fuel, the ramjet would collect interstellar hydrogen from the medium through which it travels, using an enormous electromagnetic scoop, a magnetic funnel potentially hundreds of kilometers in diameter, and burn it in a fusion reactor. In this architecture, the energy source is the interstellar medium itself, inexhaustible over the scales of the journey. A Bussard ramjet could, in principle, continue to accelerate at 1g indefinitely, and at 1g of continuous acceleration, the crew would feel normal Earth gravity. Relativistic effects would be exploited to compress the experienced journey time dramatically, and destinations across the galaxy become accessible within a single human lifetime. The physics community spent several decades examining this concept before the consensus shifted. The critical problem, identified in detail through work by theoretical physicists including Peter Fishbeck and Tees, Komarov in the 1970s, is that the proton-proton fusion cycle that would need to power the ramjet is extraordinarily slow, so slow, under the temperatures and pressures achievable in any realistic reactor, that the energy generated is actually less than the energy required to collect and heat the fuel. The ramjet, under detailed physical analysis, is almost certainly not a viable architecture. The interstellar medium is too thin, the fusion too slow, and the energy balance too unfavourable. This is a case where the dream was elegant and the physics was not. There is an alternative, the ramjet variant proposed by Daniel Whitmire in 1975, in which the collected interstellar hydrogen is not fused, but instead used as reaction mass for a laser-augmented nuclear drive. This avoids the slow fusion problem by using onboard nuclear power rather than fusion of the collected protons. But it reintroduces the onboard fuel problem to a partial degree, and the engineering of a magnetic scoop, hundreds of kilometers in diameter, travelling at a significant fraction of light speed, introduces structural challenges that make the Daedalus fusion pellet drive look straightforward. And then, briefly, there is the theoretical possibility that has generated the most public excitement and the most scholarly caution, the Alcubierre drive. In 1994, Mexican physicist Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity, presenting a solution to Einstein's field equations that described, formally, a configuration of space-time capable of moving a spacecraft from one point to another faster than light. Not by moving through space at superluminal speed, which is forbidden by special relativity, but by contracting space ahead of the ship and expanding it behind, creating a warp bubble within which the ship sits at rest, while the bubble itself moves through space at arbitrary speed. The mathematics of the Alcubierre metric is unambiguously correct as a solution to Einstein's equations. The problem is the physical requirements. To create and sustain an Alcubierre bubble of useful size, the metric requires exotic matter, matter with negative energy density. Such matter is, as far as current physics can establish, either non-existent in the universe or so rare and difficult to create or harness that it is effectively inaccessible. The amount of exotic matter required in Alcubierre's original 1994 formulation was equivalent in magnitude to a mass several times that of Jupiter with a negative energy density, a quantity so extraordinary that physicists have treated the concept more as a mathematical curiosity than a practical engineering blueprint. However fascinating the theoretical structure, subsequent work has reduced the theoretical exotic matter requirement by many orders of magnitude from the original Alcubierre estimate, through various modifications of the metric geometry. But even the most optimistic current analyses still require negative energy in amounts that exceed anything experimentally demonstrated, and most physicists consider the creation of a macroscopic warp bubble a physical impossibility pending a fundamental revision of our understanding of quantum field theory, general relativity, and the vacuum energy structure of space-time. The Alcubierre drive represents, in my view, the outer boundary of where genuine science shades into genuine speculation. It is not impossible in the sense of contradicting known physics, but it is also not possible in the sense of being achievable by any architecture we can currently contemplate, and describing it as a solution to the distance problem conflates mathematical existence with physical accessibility in a way that is not useful for honest thinking about interstellar travel. What we are left with, after working through the full spectrum of propulsion concepts, chemical rockets, nuclear thermal rockets, nuclear pulse drives, laser sails, fusion ramjets, Alcubierre metrics, is a picture both clear and sobering in its outlines. None of the architectures that are physically achievable, using principles whose physical reality is demonstrated and not merely theorized, can deliver a crewed mission to Proxima Centauri within a single human lifetime while respecting the energy and mass budgets available to a civilization at our current level of technological development. The unmanned probe at relativistic speed, a la breakthrough starshot, is the most tractable near-term option, and even it demands a 100 gigawatt laser array, a miniaturization of instruments to gram scale, and a tolerance for a mission whose total information return will be measured in hours of direct observation. This is the full weight of the distance to Proxima Centauri, not just 40 trillion kilometers, not just 74 0 years at Voyager speed, but a problem that, when examined in full engineering and physical detail, reveals itself to be one of the most comprehensively difficult challenges our species has ever confronted. Not because any single element of it violates physics, but because every element of it simultaneously demands the best our science, our engineering, our institutions, and our cultural endurance can provide. And then, when you have internalized all of that, when the full weight of the problem is properly felt, something else happens. You find yourself not defeated. You find yourself, perhaps unexpectedly, more motivated, because the precision of a well-defined problem is a kind of comfort. And the history of our species is, in the final analysis, the history of confronting precisely this kind of problem, the kind that seems, at first examination, to exceed the capacity of human beings, and that is eventually solved not by a single genius or a single mission, but by the slow, collective, multi-generational accumulation of knowledge, capability, and will. There is a particular moment in the history of every great scientific problem when the character of the challenge shifts. When the question moves from "is this possible in principle?" to "how do we actually begin?" That moment is characterized not by a breakthrough in the conventional sense, not by a single discovery that dissolves the problem, but by a crystallization of the problem's structure that makes systematic progress possible. We are in the study of interstellar distance and what crossing it requires, approaching that moment. Not at it yet. Approaching it, the James Webb Space Telescope, operating at the second Lagrange point 1, 5 million kilometers from Earth, has reshaped what is possible in exoplanet atmospheric characterization. For planets around nearby red dwarfs, Webb is probing the transmission spectra of transiting planets at a precision that would have been considered unreachable a decade ago. The TRAPPIST-1 system, a red dwarf at 40 light-years hosting 7 roughly Earth-sized planets, 3 of them in the habitable zone, has been extensively observed by Webb, with initial results placing constraints on the atmospheric properties of at least the innermost planets. These constraints are, at present, mostly upper limits. We know that TRAPPIST-1b does not have a thick CO2 atmosphere, for instance, because such an atmosphere would have produced a thermal emission signature that Webb's MIRI instrument did not detect. The absence of signal is itself data. Proxima b does not transit its star as seen from Earth, or at least no transit has been detected, and the probability of a transit geometry is estimated at roughly 1.5% based on the orbital parameters. This is a source of genuine frustration to the community, because the transit spectroscopy method that Webb uses is dependent on having a transit to observe. Without a transit, the information content available to current instrumentation about Proxima b's atmosphere is severely limited. The extremely large telescope, the ELT, currently under construction on Cerro Armazones in the Atacama Desert, with a projected first light date of 2028, may change this landscape significantly. With its 39.3-meter primary mirror and its high-contrast imaging and spectroscopy instruments, the ELT is designed to directly image reflected light from nearby exoplanets, including potentially Proxima b, and to perform high-resolution spectroscopy of that reflected light to search for atmospheric signatures, the spectral fingerprints of molecular oxygen, ozone, methane, carbon dioxide and water vapor would, in the right concentrations and combinations, constitute what atmospheric scientists call a biosignature, evidence of chemistry that is most naturally explained by the presence of life. If the ELT can detect a biosignature in Proxima b's spectrum, if the planet has an atmosphere, and if that atmosphere contains molecules in proportions consistent with biological activity, the pressure to understand that detection will be unlike anything the scientific community has previously experienced. A tentative biosignature from the nearest star would not be a scientific result. It would be a civilizational event. The implications for theology, philosophy, politics, and the allocation of scientific resources would cascade outward through human culture in ways that are difficult to fully anticipate. It is worth being precise about what biosignature means in this context, because the term carries connotations that may outrun its technical content. A biosignature in atmospheric spectroscopy is a detection of molecules or molecular combinations that are thermodynamically unstable under abiotic conditions, that would, in the absence of a continuous biological production mechanism, react away on timescales short compared to the planet's age. Oxygen, for example, is a highly reactive molecule that binds readily to iron, silicon, and other crustal minerals. Its persistence in Earth's atmosphere at 21% concentration is directly due to the continuous photosynthetic activity of billions of tons of plant and bacterial life. Without that production, atmospheric oxygen would be depleted within a few million years. Geologically rapid, the detection of oxygen in a planetary atmosphere is therefore, in principle, evidence of a biological process sustaining it. But in principle is doing work here, because there exist abiotic processes, photolysis of water vapour by ultraviolet radiation, followed by hydrogen escape to space, that can produce modest quantities of atmospheric oxygen without biology. On a planet that has been exposed to the high UV flux of Proxima Centauri for billions of years, abiotic oxygen production might be non-trivial. A detection of oxygen in Proxima B's atmosphere would be extraordinarily significant. It would not be definitive. The scientific debate would be fierce and prolonged. And that debate, the detection, the uncertainty, the argument, the design of follow-up missions to confirm or refute, would be the engine of the next phase of the human relationship with interstellar distance, because the only way to resolve the debate definitively and beyond reasonable scientific dispute is to go there. This is the peculiar self-reinforcing structure of the interstellar exploration problem. Every advance in our ability to study Proxima from here increases the urgency of going there. By giving us more information about what is worth going to see, we are currently in the phase of remote sensing, peering across 4 light-years with increasingly refined instruments, extracting what information we can from the whispers of light and gravity that the Proxima system sends our way. Each refinement in that remote sensing capability narrows the uncertainty and sharpens the question, and sharper questions are harder to ignore. Fusion propulsion concepts that have been seriously studied, from Daedalus in the 1970s to more recent proposals under investigation by organisations like the Tau Zero Foundation, the British Interplanetary Society's Project Icarus team, and various university-based research groups, all depend on a fusion technology that, in terrestrial application, has been the subject of research for over 70 years without achieving the commercial viability that was repeatedly predicted to be 20 years away. But the landscape has changed. In December 2022, the National Ignition Facility at the Lawrence Livermore National Laboratory achieved fusion ignition, a condition in which a fusion reaction releases more energy than the laser energy delivered to initiate it. For the first time in history, the margin was small, 315 megajoules of fusion energy output against 2.05 megajoules of laser input delivered to the target. But ignition was achieved, the threshold was crossed, and in 2023 and subsequent tests, the margin was improved. Commercial fusion ventures, Commonwealth Fusion Systems, TA Technologies, Helion Energy, are now operating at a scale and with a capitalization that would have been unthinkable a decade ago. Helion Energy has a contract with Microsoft for the delivery of fusion-generated electricity by 2028, with financial penalties if the deadline is missed. Commonwealth Fusion has raised over $2 billion in private capital. These are no longer purely academic research programs. They are commercial enterprises with specific delivery commitments and investor-driven urgency. Whether any of these approaches leads to the specific kind of high-performance fusion drive that an interstellar mission would require, one capable of generating exhaust velocities of thousands of kilometers per second while maintaining structural integrity across years of operation, is deeply uncertain. Terrestrial fusion power and interstellar fusion propulsion are related but distinct engineering problems, the way that a diesel generator and a cruise ship engine are related but distinct. The underlying physics is shared, The engineering requirements are specific and demanding in their own ways. What is less uncertain and more encouraging is the trajectory of scientific computation and system simulation. The ability to model plasma dynamics, material behavior under extreme conditions, and complex multi-physics interactions, which underlies both fusion reactor design and spacecraft propulsion engineering, has improved dramatically with the exponential growth in computing power. Problems that required decades of experimental iteration in the 1970s can now be substantially explored through simulation before significant physical hardware is committed. This does not eliminate the need for experimental validation, but it compresses the iterative loop between concept and testable design. The 100-year timeline from here to an operational interstellar probe, which feels like a statement of comfortable impossibility when stated boldly, is examined against the actual rate of progress in propulsion, computing, materials science, and observational astronomy, not unreasonable. 100 years ago, in 1926, Robert Goddard launched the first liquid-fueled rocket in human history, a contraption 3.5 meters tall that flew to an altitude of approximately 12 meters and a range of 56 meters. 43 years later, humans walked on the moon. The acceleration of capability in the intervening century has been of a character and magnitude that makes a 100-year projection to interstellar probe capability. While not a certainty, not an idle fantasy, what I think is genuinely plausible looking forward is not a single dramatic mission but a sequence of capability milestones, each one preparing the ground for the next, in a way that is more analogous to the history of aviation. From the Wright Flyer in 1903 to the Boeing 747 in 1969 in 66 years, than to the narrative of Apollo, which was a sprint to a single destination. The interstellar journey will be a marathon. It will proceed through solar sail demonstrations, then laser sail tests in the inner solar system, then gram-scale probe tests to 0 astromiles, then perhaps 10,000 astromiles, building confidence in the technology at each stage before committing to the full 4.2 light-year mission. And in parallel with the propulsion development, the observational program will continue to sharpen the target. By the time any probe is ready to fly toward Proxima Centauri, we will likely know, from the ELT, from space-based direct imaging missions, like the proposed Habitable Worlds Observatory, whether Proxima b has an atmosphere, whether that atmosphere is thick or thin, whether it contains biosignature-compatible chemistry, and what the magnetic and particle environment of the system looks like in substantial detail. The probe will not fly blind. It will fly toward a destination that has been studied for decades, whose physical character is understood with a precision we can barely imagine from where we stand now. This is the nature of the next horizon. Not a single leap across the void, but a careful, cumulative, multi-generational advance in which each generation adds a layer of capability and knowledge until the moment arrives when the first probe departs for the nearest star, carrying with it the accumulated intellectual inheritance of everyone who asked the question before it. On the 12th of February 1990, with Voyager 1 at a distance of approximately 6.4 billion kilometers from Earth, and about to pass beyond the plane of the planetary solar system, the mission team executed a command sequence that had been proposed years earlier by Carl Sagan, and that NASA management had initially resisted as scientifically unproductive. They turned the spacecraft around and took a photograph of the solar system, the full family portrait, a mosaic of 60 frames spanning 6 hours of imaging time. In one of those frames, slightly more than a single pixel, suspended in a band of scattered light from the camera's optics, was Earth, a pale blue speck, barely distinguishable from the noise of the image. And Sagan wrote about that photograph in words that remain, more than 3 decades later, a precise articulation of why the distance to Proxima Centauri matters not as an engineering problem, but as a statement about our situation in the cosmos. "Our planet is a lonely speck," he wrote, "in the great enveloping cosmic dark. In our obscurity, In all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. There is a way of reading that passage as pure pessimism, a counsel of smallness and resignation. I read it differently. I read it as the clearest argument ever made, in the fewest possible words, for why the distance to the nearest star is not merely a scientific or an engineering problem. It is the central fact of our species' current situation. We are, as a matter of physical reality, confined to a single pale speck. Everything we love, everything we have built, everyone who has ever lived, the whole of human civilization, every work of art and science and music, every child, every city, every grief and every triumph, is located on one object in one solar system, orbiting one of perhaps 400 billion stars in one of perhaps 2 trillion galaxies. The distance to Proxima Centauri is the first step out of that confinement, not the last step, not the solved problem, the first step. And the fact that the first step is this difficult, that it demands not just better rockets but better institutions, not just more energy but more patience, not just superior engineering but a kind of cultural will that our species has not yet fully assembled. This does not diminish the aspiration. If anything, it clarifies it, because the distance to Proxima Centauri is, in the deepest sense, a mirror. When we look at those 40 trillion kilometres honestly, when we work through the engineering, the physics, the biology, the ethics, the institutional challenges, we are not learning about the universe. We are learning about ourselves. We are learning what kind of species we currently are and what kind of species we would need to become to cross that gap. The distance is a measure of our limitations, yes, but limitations are descriptions, not verdicts. They describe the gap between what is and what must be built. Something that I find myself returning to, again and again, is the image of Guillem Anglada Escude's team in the Atacama Desert in the southern autumn of 2016, collecting 60 hours of data from a star they could not see with their naked eyes, hunting a signal smaller than the sound of their own footsteps, in a building where the equipment had been tuned to a precision that earlier generations of scientists could not have imagined. They did not know, when the campaign began, whether the signal was real. They did not know whether the years of earlier hints represented a planet or a star's restless magnetic surface fooling them again. They sat with the uncertainty, and they kept observing. That patience, that willingness to maintain vigil over a question whose answer might not come, or might come years after you expected, or might not be the answer you hoped for, is perhaps the most human thing in this whole story. It is the same patience that kept medieval astronomers charting the sky before telescopes, and that kept Bessel pointing his instrument at 61 Cygni in 1838 until the parallax shifted by 0.3 arc-seconds, and the first stellar distance was measured, and that keeps physicists at the NIF firing laser pulses at pellets of deuterium-tritium, until ignition is finally achieved. The distance to Proxima Centauri is 40,208,000 kilometres. It is worse than you thought in every technical and engineering dimension we have examined. The fuel requirements are vast. The radiation is lethal. The dust is destructive at speed. The destination may or may not be a world in any meaningful sense. The institutional requirements exceed our current capacity. The ethics of generation ships resist easy resolution. The fastest physically credible propulsion concepts will still require decades to develop to operational readiness, and they will not carry a crew. And yet there is a world there, possibly, a mass in a zone where water could exist, orbiting the nearest star 4 years and 3 months of light travel away. We know its period to 4 significant figures. We know its minimum mass. We know the radiation environment it sits in. We know, within broad bounds, whether it might be tidally locked and why that matters. We know far more about the nearest star system than any human being who ever lived before 1915, when Robert Innes first measured that telltale proper motion and knew, without yet fully understanding what he was knowing, that something was close. Each generation measures the distance more precisely and understands the problem more completely. This one found the planet. The next one will tell us whether it has air. The one after that will send the first probe, and the one after that will receive the first data 4 years after departure. And somewhere, far down the line, in a year that belongs to people not yet born, something humanity built will arrive at the nearest other sun, cross the space between its planets, and look, really look, at a world that orbits a star that is not our own. We are not that generation. But we are the one that made the distance honest. The question is now properly sized. Carry it forward,